Hi, I'm Ed Sperling. I'm the Editorial Director of Low Power High Performance Engineering. I'm here with Aart, the Chairman and CEO of Synopsys. Aart, what does the industry look like in 5 years?
When you're talking about the industry, I assume it's a combination of semiconductor industry, EDA industry, maybe even hardware, software industry.
Yes.
Because after all, they're one, right? And actually, that characterizes the very thing that's at the center of this change, which is the interdependence between the skill sets ranging from deep understanding of silicon all the way to the utilization of IP blocks, the design flows verification, to the hardware software. And the way I would characterize the industry is that the companies that will do well are the ones that execute well against systemic complexity, not just scale complexity, Moore's law, of which we will still have 5 years of more capabilities. Don't get me wrong, Moore's law is not dead. But at the same time, systemic complexity means that you have to bring all the skills together to actually make very sophisticated chips that contain IP from a variety of sources, etc. And so if you look at forecasting the industry, one of the angles will be to understand which ones are the companies that actually manage to bring that all together. Now, that also includes driving some of the advanced nodes. And so in 5 years, we will see quite a bit of design at the 20 nanometer node, which today is still quite a bit of a challenge for some.
Does hardware drive software or does software drive hardware?
Well, it is actually a more complex question than you may have thought, because one can argue both sides. There's some hardware that drives software. And the reason I'm saying that is if you look at the evolution of chips right now, for starters, what you see is that most chips have multiple computational cores. And actually, they may be very different cores. There may be general purpose cores, there may be graphics processor, general purpose cores, DSPs, and so on. And the fact that I say multiple right there gives an enormous challenge to the software, meaning that how to write effectively software that runs on different cores, that adapts itself to the circumstances, is an interesting and very promising challenge. I can flip it around in a second the other way and say, oh no, software is going to drive hardware, because there are many applications that do very sophisticated tasks over and over and over again. And therefore the question is, well, for those tasks, would it not be okay to have specialized hardware? And you can see this starting to happen in the server business right now. There are multiple people saying, oh, you know, we are starting to develop chips just for some applications. Perfect example of that is the fact that Oracle bought Sun. Well, they said, hey, if we do that, we can provide both the software, the application software, and the hardware, and optimize one for the other and vice versa. With other words, there too, systemic complexity is not just within a chip. It is actually between the applications and the hardware that implements it. So the answer is yes and yes.
You know, for the past 5-10 years, what we've been watching is developments that happen in the mobile space make their way up into the corporate enterprise. It looks like it's starting to happen in reverse now, where some of the developments that are happening in the data center are coming down into the mobile space. What's driving that?
Well, you know, I think in all the high-end or high-volume areas, and I would put both the networking, the server, the of course mobile there. Time to market is always very, very important. But it is, of course, more so on the mobile space. There, the race is absolutely on. And the fundamental trade-off is how much performance can I get out of the power that my battery will give me for a day. So the power is the limiting factor. And the more you can optimize for power, the better. Interestingly enough, that same concept, although in a different magnitude, is happening in the server space as well. And the reason is quite simple. You look at the server farms that are being built, they're limited by how much power can they bring in. Are you next to a nuclear power plant or so? And how much cooling can you afford? Are you next to a river? And that's maybe overstating it a little bit. But the fact is, people are starting to think in those terms. And so if you can impact the power utilization of the processors that are in the servers that are all driven for maximum performance, even a little bit, that has massive economic impact. And that's why there too, the performance power trade-off is absolutely at the center of everything our customers and therefore we have to do.
You mentioned Moore's law looking out 5 years. What happens after that? Does it continue, or does it break? And does it break because of technology, or does it break because of business?
Well, the answer has to be yes, but multiple times. And it's been yes for many, many years, meaning that the death of Moore's Law has been forecasted every 5 years or so. And the interesting thing is that despite all these forecasts, I think the sheer engineering ingenuity has brought about yet another way to do it differently. And you see it in action right now as we speak. The fact that we're now seeing every one of the top semiconductor manufacturing companies investing massively in FinFETs, transistor that certainly is vertical, and that also has the benefit of lower leakage, is a testimony that, hey, we never give up in our field. Having said that, the economics do matter. And if we look at where Moore's Law is today, the old rule, somewhat overstated maybe, that every new generation would give you more transistors at half the price per transistor is no longer true. Essentially, the return of investment for new nodes per transistor has significantly diminished. Now you'd say, well, if that's the case, why would you go to smaller geometries? Because of the other benefits, the benefits of power I just mentioned, but also another benefit, which is smaller transistor still allows you to put more transistor on the same space, and more transistor means higher integration of functionality. And that is of prime value when you're differentiating your high-end phone with a super high-end phone. The more capabilities you have for the same amount of power and area, the better.
The reality, though, is that there are fewer companies now at the leading edge. What does that mean for EDA?
Well, I think there's no question that staying at the leading edge is hard. There may be a little bit fewer, but there's also more intensity at that leading edge, partially because the prizes are very high if you win. And you mentioned earlier, the mobile world. This is a world with enormous volume that in a moment's notice can really go up dramatically. And then you want to have the capabilities and the capacity to play. Having said that, the complexity is growing, both in terms of scale complexity, Moore's Law, and systemic complexity. And therefore, what it means for EDA and specifically for Synopsys is that we need to have a lot of skills that all come together at the same time, including coming together with the customers doing the design. With other words, we're very much a team. Now, I always like to say that our tools at this point in time, like race cars, they may be difficult to drive, but they do drive really fast. And our customers are the race car drivers that are trying to win the Grand Prix of the most advanced chip. Well, they also know that they need a pit crew. And we also provide the pit crew. That's our support team. And as you know, if the driver doesn't listen to the pit crew, they have no chance because they'll miss the fact that they have to change tires at a certain temperature and so on. The same is true for chips. We have support teams that can help our customers absolutely get the best results on an advanced ARM core in terms of performance and power, for example. And we work, of course, with very, very good designers. And so that's team play right there. And that includes, of course, understanding the race car that allows you to drive through this incredible competition.
When I look at the industry and I look at all the big EDA players, what I see happening is there seems to be a lot more focus on integration of existing tools rather than development of new tools for new things. What's driving that?
Well, the reason you have that impression is because you're seeing actually the results of a push, certainly on our part at Synopsys, of about 10 years in that direction, which is that we diagnosed 10 years ago that we had two pathways to take simultaneously. One was better, faster, cheaper, more capability, tools, you name it. No end to that, right? And that's sort of the Moore's Law, or what I call the scale complexity part. There's no end to that. And by the way, an enormous amount of innovation is going into that. Not only from better algorithms, but also dealing with phenomena that just a few years ago we didn't have to deal with. Multiple illuminations on the same mask, for example, to get the small feature sizes. So that was one thrust. The second thrust, though, was the recognition that when you deal with a chain of tools, that you can have great tools and bad results if these tools don't work well together. And a prime example that I'm really proud of what was accomplished was actually between synthesis and place and route. You know, I always think of synthesis, that's a logical part of optimization, and place and route is the physical part. Well, what we did was take some of the physical part, move it into the synthesizer, specifically the ability to have some placement, therefore to know the distances, therefore to know the delay, and therefore synthesize things that then would place and route better. As a matter of fact, we took even some of the routing and put it in the synthesizer. And because of that, we could actually diagnose in the synthesis already if there would be the danger for congestion. Well, congestion is a killer, meaning that if you find that you have congestion and you're now 1 month away from tape out, you're not going to be in a good mood, because that means you have to go way back to the floor plan, to rearranging blocks in order to get out of this congestion. Not any different than being in traffic and suddenly saying, well, I'm going to drive to another neighborhood. Well, no matter what, you don't win, right? And so the fact that the synthesizer can anticipate, and I love to call it clairvoyant, what's going to happen downstream is an awesome accomplishment. But it's a great illustration that these are not independent tools. They have to work together. And in order to do that, by the way, they need to have the same understanding of timing and of power and a number of other metrics for optimization. And that's why the combination of being really well tuned for each other and best in class is so important. And you can find examples like that in everyday life too. You know, it was possible long before Steve Jobs introduced the iPod to download music, play it on an MP3 player, pay for it. It just never quite worked. You would send the money and the thing wouldn't arrive, the player wouldn't read the music. And by the way, he also happened to get the providers of music to agree on 99 cents as the price. What an accomplishment. Well, fundamentally what he did was to align a whole food chain of events to make the end result really good. We're doing exactly the same in a hyper-complex environment, which is the design of chips, which are arguably among the most complex things humankind have ever designed.
When you look out over the next few years, what do you see as the biggest bottlenecks in design?
Well, you know, the problem spots have really not changed, as far as I can tell, in the last 15, 20 years. And the reason I'm saying that is because, sure, there's always new challenges and new problems and so on, but we can deal with all of them. And the minute you deal with them, somebody throws a curveball, and it's always the same curveball. Well, if you can do that, why don't you do it with a little higher performance, a little lower power? Well, haven't we heard this one before? Yeah, over and over again, which is just another way of saying, well, I just gave you a brand new race car. You know, it's really better, it's easier to drive. You take it for a spin, and yes, it is. And then the next question is, could I go faster? Because you still want to win, right? And the faster in the context of what we do invariably is performance, power, performance, power, performance, power. That is the driver for high tech in the semiconductor industry. Now, around that, there are all the things like the 3D stacking and the new silicon technologies and the FinFETs. Those are all fun problems. They're all aimed at the same thing, which is this performance, power. And of course, the third one in the trio is cost, which is always there. And maybe the fourth one is, oh, and by the way, sooner, right? Which is winning the race.
Aart de Geus, thank you very much for your time.
You're most welcome.